So here is a short video on reading two component pressure composition and temperature composition phase diagrams. Keep in mind Raoult's law here. So here is a typical pressure composition phase diagram. On the x-axis, you have the mole fraction of component A, which I'm going to call ZA. I recommend not using the notation in Atkins because it is a bit confusing. So when the mole fraction of A is 0, then what you have, the pressure on the y-axis is the vapor pressure of component B. Here we are assuming that we have a mixture of A and B. So this pressure is PB star. And when the mole fraction of A is equal to 1, then the total pressure is equal to the vapor pressure of pure A. And then of course there is a straight line connecting these two. Now at high pressures, so anything above this red line, what you have is the liquid phase. And between the red line and this line here, you have two coexisting phases. So you have liquid plus vapor. At very low pressures, you only have the vapor phase. Okay, so now we'll try to read these plots and how you can find the composition of a mixture at starting from a given mole fraction of A. So let's say you start here at point A, and the initial composition of the liquid in the liquid phase, the mole fraction of A is equal to ZA. Now you start lowering the pressure. At some point when the pressure becomes low enough, some of the mixture will start to form a vapor. And this will be the composition of the vapor. There will be a very little minuscule amount of vapor here. If you decrease the pressure further, you come in this region of two-phase coexistence. And let us say you are at this point, and then you want to measure the composition of the liquid phase and the vapor phase. And then you draw what is called a tie line. And the point at which it intersects the black curve will be the composition of the vapor phase, and the point at which it intersects the red curve is the composition of the liquid phase. So let us try to calculate XA and YA, or the relationship between them. The total number of moles multiplied by the overall mole fraction of A must be equal to the number of moles in the liquid phase multiplied by the mole fraction in the liquid phase, and that is equal to XA plus the number of moles in the vapor phase multiplied by the mole fraction of A in the vapor phase. Also, the number of moles multiplied by the overall mole fraction of A must be equal to number of moles in the liquid phase plus number of moles in the vapor phase multiplied by the overall mole fraction. This is equation 1 and this is equation 2. From these two equations, you can write number of moles in the liquid phase multiplied by the mole fraction overall plus the number of moles in the vapor phase multiplied by the overall mole fraction. So I have taken this and I have substituted it here. And this is equal to the number of moles in the liquid phase multiplied by the mole fraction in the liquid phase plus the number of moles in the vapor phase multiplied by the mole fraction in the vapor phase. I can rewrite this equation such that the number of moles in the liquid phase multiplied by ZA minus XA, so I bring this to this side, is equal to the number of moles of in the vapor phase multiplied by YA minus ZA. Now if you look carefully, ZA minus XA is the length of this line here. So let's call this length of the liquid phase tie line, and YA minus ZA, this distance, is equal to the length of this tie line, and we are going to call it length of the vapor phase, length of the tie line in the vapor phase. Then we can rewrite this equation: the number of moles or the amount in the liquid phase multiplied by the length of the tie line of the liquid phase is equal to the number of moles in the vapor phase multiplied by the length of the tie line in the vapor phase. What does this tell us? This tells us that the number of moles in the liquid phase is proportional to the length of the tie line of the vapor phase divided by the length of the tie line in the liquid phase. So the longer the length of the tie line for a certain phase, the smaller the amount of that phase. This is called, you probably know, the Lever rule. Okay, so this is a pressure composition phase diagram. One can also draw a temperature composition phase diagram where you have temperature on the y-axis and the mole fraction of A on the z-axis. I'm sorry, on the x-axis. And in this case, as you will see in the other video, the phase diagram looks approximately like this. At high temperatures, you only have the vapor. At low temperatures, you only have the liquid. In between, in this region between these two curved lines, you have the phase coexistence region. I will now give you a very short illustration of how distillation works. Let's say you start with a composition XA1 in the liquid phase and you start heating this. As you start heating it, at some point you will touch the phase coexistence region, and at this point, I'm sorry, that line is not very straight. I will try to reconstruct it. You can see that the vapor at this point is much richer in A, has a much higher mole fraction of A than the composition that we started with. So if one can take all this vapor and recondense it, for recondensing you will cool it a bit further, and you reach this point which has a higher mole fraction of A, and then you can repeat the process. So you can go further here